Hello, physics fans. Last time that we were together, we should have, had you not been asking such great questions, gone through a couple of examples with torque, and I wanted to make sure that you had the opportunity to see those before you started working on your problem set. So here we go. I would encourage you to have some textbooks out, calculators out, follow along with me as if I was standing in class with you, just so that you can make sure that you really understand this stuff. The first question that I'm going to look at is on page 282, and it is number 1. Before I actually get started, I just want to remind you of a couple of things that we talked about last time. Last time we were together, we defined that thing called torque. It is describing something going through rotational motion, so accelerating, speeding up or slowing down as it rotates. We said that it was a force acting a certain distance away from an axis of rotation, and we said that those two things had to be perpendicular to each other in order for that torque to happen. So hopefully that makes sense. We'll keep talking through it as we go, but that was the thing that I wanted to make sure you kept in mind. So question number 1 says, find the magnitude of the torque produced by a 3 Newton force applied to a door at a perpendicular distance of 0.25 meters from the hinge. So if we work through this, I'm going to just draw a picture here. This is kind of like a problem that we talked about in class. So notate that is not a doorknob. This is actually a door this time. There's a force acting, a 3 Newton force, perpendicular distance of 0.25 meters. So I'm going to apply a force in this direction, F sub A, okay, and it's at a distance, a radius of 0.25 meters. So R is equal to 0.25, and the force is equal to 3 newtons. We're going to go ahead and put that into our equation to find the torque, which is just the force times the radius, and there it is perpendicular, so we really can just multiply, and that'll give us 0.75 newtons times meters. And remember, we said that that's a newton times a meter. It's not a joule. We're just going to leave it as a newton times a meter. That's a pretty straightforward question, eh? Let's try another one. Let's take a look at number 2. I'm going to go through number 2A with you. Number 2B is one that I'm going to let you work on as part of your problem set, but it will look very similar. Okay? So number 2A says a simple pendulum consists of a 3 kilogram point mass hanging at the end of a 2 meter long string that's connected to the pivot point. So let's go ahead and draw ourselves a picture of this. So there's like a ceiling, and here is my string with my mass right here, okay? And we know a couple of things. We know this distance here, R is equal to 2 meters. And we also know that the mass of the object is 3 kilograms. In part A, it asks us to calculate the magnitude of the torque due to the force of gravity around the pivot point when the string makes an angle of 5 degrees with the vertical. So there's a lot in there. Let's kind of figure out what's going on. So we know that this angle here, theta, is 5 degrees. So that's nice to know. And then I'm going to go ahead and draw some forces acting on that mass, because I think that that's going to be a nice way to look at what's going on. So if we were just going to draw a free body diagram, even if we weren't looking for torque, we would know that there's a force going down. That's the force of the earth on the mass, Fg. And we know that there's a force of the string pulling, I want a new color, there we go, up in this direction, Ft, a tension force. So I could, if I was going to be a really good kid, and why not, let's do force of the string on the mass. So you'll notice in the question that it says the magnitude of the torque by the force due to gravity. They didn't even actually have to tell you that, because the force on the mass of the string on the mass, that one, if you'll notice, is going in the same direction as the string. So there is no component of that is going perpendicular to the radius. So the string on the mass does not provide any torque. The force of the earth on the mass does provide torque, but it's not the entire force that provides the torque. It's only the part that is perpendicular to the radius. So we need to break the force of gravity into components. We've done this before. It's kind of like we did on the inclined planes, if you remember those. That was a little while ago. We can do one that's going this way and one that's going this way. The key here, and I don't want you to forget this, is that the force of gravity, the one that you're breaking into components, has to be the hypotenuse of the triangle. So if I zoom in a little bit so we can really see what's going on, this is the right angle, and this angle here we can look at using our fancy geometry skills. We know that that's also going to be theta. Okay, so this part right here is FG times the sine of theta. That's where that sine of theta comes from in the equation, the way it's written in the book, if you remember that one. So make this about the right size again. Now we can find that torque. The torque is equal again to the force times the distance, the radius away, making sure that they're perpendicular. So this is going to be m times g, that's the force of gravity, because that's what force is causing the torque, times the sine of the angle theta, okay, times the radius, that's the 2 meters. So now if we plug that in, we've got 3.0 kilograms times 9.81 meters per second squared. We don't need the negative sign because we're taking care of all of the directions in our problem itself. We've got the sine of 5 degrees, and then the radius is 2. That's a lot of things to multiply. I'll let you pull your calculators out and do it. I'm going to do it too so that we can compare our answers. Click, click, click. Can you hear it going? And I get something like 5.1 newtons times meters. It's a little bit funny to say that, but again, we have a kilogram meter per second squared, that's a newton, and then times a meter gives us 5.1 newton meters. So hopefully those two questions have made sense. The other two pieces on 282 are ones that I would like you to work on as part of the problem set. I'm going to leave those for you to do. The sub does have copies of solutions for those. If you want to check them, that would be a great idea. All right, we're going to look at one more problem together so that you are feeling comfortable with this when we start, or when you start doing the rest of your problem set, because there are a lot of these problems out there, and I really want to make sure they make sense. We talked about some of this idea last time we were together, the idea of rotational equilibrium. Q-U-I-L-I. I spell so well, not really. The idea of rotational equilibrium, hopefully we remember this. We know that something's in equilibrium if the net force acting on it is 0. That's going to result in an acceleration of 0, and that means that it's not going to speed up or slow down, but that's in a straight line motion. We also, hopefully, you remember, we got ourselves to believe that the net torque is also a vector, is equal to 0, and if the torque is equal to 0, then it's not going to speed up or slow down in its rotation. And later we'll talk about the angular equivalent to acceleration, but for now, that's the thing you need to remember. The equilibrium systems that we're going to look at today are ones that are not moving. So those are easy to look at, easy to conceptualize really what's going on. The problems that we're looking at are lovingly known by many physics students as bridge problems, and it's nice that the question we're going to look at together is, in fact, a real bridge problem. So you're going to look at page 288, and I'm going to take a look with you at number 2. This question is fairly straightforward, but there's a lot to it. So I really want you to pay attention, work through it with me as we're going so that you understand the process so that you can do the rest of the problems today. And this will actually lead you into the work that you will do on the next day, depending on which, if you're an A day or B day, in the lab. So pay attention, listen up if you're not already. Okay, it says that we have a uniform bridge that's 20 meters long and weighs 4 times 10 to the 5th newtons. I'm going to do this one little bit at a time so that we really understand what's going on. So here's my bridge. 20 meters long. I'm going to give myself just a little more space up here. So this is 20. Okay. And it has a weight, which means it's not the mass, but it's actually the force of gravity acting, right? The force of gravity for the bridge is 4.0 times 10 to the 5th newtons. We know that that has to be the weight because it's measured in newtons, not in kilograms. So it says that it's supported by 2 pillars. Each pillar is located 3 meters from each end. So if we go ahead and put those pillars, one of them is going to be here. I'm going to call that one pillar 1. And this distance here is 3 meters. And I'm going to put pillar 2 over here. Not necessarily drawn to scale, but you get the idea. I'm going to call that one pillar 2. That is also 3 meters away. It says, if a 1.96 times 10 to the 4th newton, so again we're talking about a weight, car is parked 8 meters from one end of the bridge, how much force does each pillar exert? So we're going to put a car, I like purple cars, so we're going to go ahead and put a purple car right here. So this is 3 meters, and I'm going to put it another 5 meters, so it's something like this, let's say. So there's my car. This is 8 meters. Okay. And the question says, how much force does each pillar exert? So we need to start looking at the forces. Forces can then lead us to the understanding of torque, so we're going to do this kind of one piece at a time. Hopefully it makes sense to you that the bridge is being pulled down. We could break it up into lots and lots of pieces that are all pulled down, or because it says that it's uniform, we can assume that all of that force is coming from the center and pulling straight down. That is called the center of mass. If you've heard of that term, fantastic. If not, just think about it as the balance point. It's the place where it is not going to tip if you just apply a force up there. So I'm going to write this as the force of the earth on the bridge. And then in parentheses, I'm going to say Fg sub b so that I don't get confused, because there's going to be another force of the earth. It's the force of the earth on the car. So I'm going to put a force up here like this. Force of the earth on the car, Fg sub c. Okay. Now those aren't the only 2 forces acting. If they were, then this whole system is going to fall straight down. No, we've got the forces of the pillars, and we know that's true, especially since the question asks, how much force does each pillar exert? The pillars are going to push up, and I'm just going to call that F1 for the pillar 1 and F2 for pillar 2. Those are not drawn to scale, they're just kind of put in there. Okay, so how do we start? Well, we know that the net force has to add up to 0, right? Because otherwise this thing would be accelerating. So let's go ahead and write down an Fnet equation. Fnet, all the forces add up together, have to equal 0. So I've got F1 plus, I'm just going straight across in this direction, okay? So I've got F1 plus FGB plus FGC plus F2. And those 4 forces have to add up to 0. Now we do need to take into account directions. So I know that FGB and FGC are pulling down. So I'm going to write this as F1 minus FGB minus FGC plus F2 is equal to 0. Now if we look at this carefully, we can see that I know this one and I know this one, but there are actually 2 things in this statement that I don't know, which means that I can't solve the problem just using this statement. I can, however, utilize the fact that not only does the force have to be 0, but for this to be in equilibrium, for this force to be in equilibrium, or the system to be in equilibrium, excuse me, then the torque also has to be 0. So I'm going to set up a statement of torque adding to 0. So the net torque is going to be all of the torques added together. So it's going to be the torque from 1 plus the torque from the bridge plus, and these all actually are vectors, so I'm going to put vector hats on them just so we don't forget that we need to take direction into account. There's the torque of the car and the torque of the pier, and those have to add up to 0. Now, remember, torque is really force times the radius. Right now we don't have a radius. So here's one of these really great opportunities, kind of like you had when you get to pick the height when you're doing gravitational potential energy. We get to pick where we want the rotation point to be. So you can pick the rotation point to be anywhere you want. There are some choices that are better than others. One clever choice would be to put the axis of rotation right here. And the reason for that, to put it right on pier 1, is because then the torque for 1 goes to 0 because the radius is 0. That's really nice because then we only have an unknown in torque 2, the force for 2. So we'll be able to solve the statement. So before we get too far, I do want to look at the directions and then the radii for the torques. So let's do the directions first. Last time we were together, I think that I told you this, but I want to make sure that it really makes sense. When we're talking about directions for torque, we can talk about the direction that the torque would cause the bridge to rotate. If the bridge itself were the only thing acting in the system, then it would cause the bridge to rotate in this direction. That is the clockwise direction, and clockwise is, by convention, a negative direction. So I'm going to make that a negative torque. The earth on the car will also cause this system to go in the clockwise direction, so that will also be a negative torque. The force of pier 2 on the bridge, if that were the only thing acting, if nothing else was acting, the bridge would go up, it would go in the counterclockwise direction, and so that is going to be a positive torque. I'm going to erase these arrows just so that my picture doesn't get any more complicated than it already is. So that's the first thing we need to do. The other little piece here is that we need to, instead of writing torques, we need to write it in terms of forces. So let me get my green pen back. There we are. Instead of writing torque B, I'm going to write negative FB, and remember we have that number, times the distance. So now we need to determine the distance between the axis of rotation and the bridge. The bridge's center of mass is at the middle, so that's at the 10-meter mark from the edge. But we're already 3 meters in, so that means that this is going to be 7 meters. Okay. I've also got a negative torque from the car, so that's going to be minus the force on the car, and I forgot to write that one down. Let me write that down in a minute. Times, let's go ahead and figure out how far away that is. So this one may take a little bit more thinking, but we can do it. You guys are smart. We know that this is 8. That distance is 8. And so there are 2 to get in here, right? So it's going to be 9 away from the axis of rotation. Hopefully that made sense to you. If it didn't, maybe talk to your neighbor and see if they can help you out. And then the last one, again, is going to be a positive torque. It's the force of pier 2. That's the thing we don't know we're trying to solve for. But then we need to find the distance. So that means we're going to look for the distance from this pier over to that pier. So if you think about it, we can look at this as it's a total of 20 meters. We're leaving out 6 total on either side, so that's going to be 16. No, 14. I can't subtract in my head today. 14 meters. I hope I did that right. 20 minus 6 is 14. Yes. So that equals 0. Now, I'm going to go ahead and plug in those numbers. I just forgot to write this down before. Fg sub c, looking back at the problem, is 1.96 times 10 to the 4th newtons. Okay? And from this then, I know everything except F2, which means I should be able to solve for it. So let's do it. So I can move these 2 over to the other side. So I have F2 is equal to FB times 7 plus FC times 9 divided by 14. And that will give me the force on 2. So I'm going to go ahead and try that. You plug it into your calculators as well. We'll compare answers in just a moment. Are you actually doing it? You should be. Plug it in. Do it. Do it. Okay. So for the force 2, I got 2.13 times 10 to the, let me count it, 1, 2, 3, 4, 5, 10 to the 5th. How'd we do? Hopefully well. If not, let me know, or don't let me know, but let your table mate know. Help each other out. Once you know this value, then all you need to do is plug it in over here for F2 and solve for F1. So that should be fairly straightforward, but let's go ahead and go through it. So F1 is going to be FGB, when we move it over it becomes positive, plus FGC, again same thing there, minus F2. So when we plug that in, we're going to use the values that we had before. So that's this one, and this guy down here. So we can go ahead and do that addition and subtraction. Oops. I got something like 2.07 times 10 to the 5th newtons. So there you go. It's kind of an ugly problem when you, on the face of it, but it really shouldn't be super hard. Again, remembering that we need to set both of those equal to 0. Hopefully this was helpful. You should be able to do all those problems that are in front of you now. Good luck. If you have major emergencies, let me know. Be well, and I'll see you soon. Bye.